What's up, guys and girls? Here we are back again for thermochemistry. Let me make sure I'm centered up a little bit. I think I am. Okay. Welcome to my classroom. Don't you love it back here? Yeah. Anyway, I'm going to pick up where we left off from Friday, and with a little overlap, pick up where I left off from the last video, actually, with a little overlap on thermochemistry, which is actually you're going to see, which is specific heat. I'm going to solve a few problems on here digitally. And then we're going to proceed a little bit more rapidly through what's going on. So buckle up. Here we go. First, we're going to begin with the same slides. We have what is specific heat. That's kind of where we're picking up from the last video, of course. And first, a good thought of heat transfer or energy transfer. Like if you stand on a cold bathroom floor, most bathroom floors with tiles, that is, it would feel very cold to your feet. Even if your house is very hot, even if your heat pump is on. So what is this about? What is this about heat, temperature, and energy? What's going on? And of course, talking about transferring of energy from your warmth to the cooler object, the floor. And there you go. Oh, you know what? Wouldn't you know it? I forgot my lower third. Nice. So here we are. Yeah, once again, thermochemistry, night chemistry. Thermochemistry number 2. Go dogs. All right, good deal. So let's continue with the notes. And so heat, remember, energy flows from something hot to cold. Hotter substance gives kinetic energy to the colder one. Kinetic energy is transferred. That is, by definition, heat. The total energy of the system, of the setup, remains the same. This is the law of conservation of energy, of course. There's no energies created nor destroyed. And then the word on capacity is how much heat is required to raise a substance's temperature by 1 degree, regardless of mass, regardless of grams, that is, right? Large versus small, obviously larger versus smaller objects of the exact same consistency. They're both made of the same metal, for example. Larger objects require more heat to raise them 1 degree. This just makes sense that you have more of it. Therefore, you have you need more heat capacity. If we get more specific, then we need to talk more about, of course, how much its identity, some sort of identity marker. So more heat required to raise a degree. So this would just be like enthalpy equals mass times delta T. If you remember from the equation from Friday, MC delta T, and you'll see soon again. So this does not go with specific heat because this is just capacity general for something to heat up 1 degree. Remember, universe, system, surroundings, universe are all things that could be quantified or given attention to at all in chemistry. System is the thing that we focus our attention on the most. So like when we talked about our feet hitting the bathroom floor, we're talking about our feet are the system, the floor is the surroundings of focus. Of course, the air is also surroundings around our feet. And so we have what we're describing is what happens in the system of our feet. Heat leaves the system, the surroundings gain it, the floor is the surroundings. So we have a loss of heat. It'll be a negative Q on our feet, which is why we feel the cold. Negative Q would be negative heat. Q, of course, is that variable that means heat, of course, for our purposes. Okay, next we have, let me keep going here. So a quick learning check. When you touch ice, heat is transferred from. When you drink a hot cup of coffee, heat is transferred from your hand to the ice and the coffee to your mouth, from the hotter to the colder substance. Okay, let's just say you take 200 grams of water and you heat it for 1 minute. You apply a certain amount of heat. Let's just call it 10 units of heat to the 200 grams of water for 1 minute. And that 10 units of heat raises the temperature from 10 to 18 degrees. What would happen if I double the amount of water to 400 grams, same pan, same 10 units of heat, starting at 10 degrees Celsius, I apply the same heat for 1 minute, 10 units for 1 minute. What would you expect the final temperature to be? It would be half the change. So 10 instead of 10 to 18 would be 10 to 14 for a change of 4 instead of a change of 8. This is because you have more water, a greater mass, twice the mass, so half the change. Twice the mass, so the capacity takes twice as much time. That case. So in the same amount of time, be half as much of a change. Replay that back if you need to hear me say that again. Twice the mass is half the change, or requires twice the time to get to the same change. Okay, heat is measured in calories and joules. Calories is just another unit. You may have heard this in food calories. Now we're distinguishing from food calories just a bit because food calories are actually considered a capital C calories right there, short for that is calories. And capital C calories equals 1 kilocalorie. A big C calorie is 1 kilocalorie, which means 1,000 calories. And 1 calorie also equals 4.18 joules. Joules is a more commonly used energy unit for heat, for energy in general. It's used across the board of all types of energy, heat, electrical, magnetic, all these other types of things that we might use heat for, gravitational energy. All those energies are used in joules, and so it's worthwhile to have that there. Although with heat, calories is oftentimes used depending on the setting. So, of course, kilojoules is also used because we have so many joules in the thousands of joules in a lot of different processes, and so we'll end up using kilojoules quite a bit. Question on specific heat. Why do some foods stay hot longer than others? Why is the beach sand hot, but the water is cool on the very same hot day outside? You know, in the middle of July, on Florida's eastern coast, at Daytona Beach, the sand is very hot, but the air is hot, but the water is still cool. Maybe not in the middle of July, maybe beginning of June, perhaps, where it's still not all the way acclimated. Okay, how can the water be cool, but the beach sand be hot? I'm sure you can think of this, or it might ring a bell. The sand and the water are two different substances. Okay, duh, right. It's not a hard thing to understand or suggest, but the water and the sand are two different substances, and the fact that they're two different substances mean they have two different abilities to heat up, and therefore heat up at different rates, right? So the term for this is they have different specific heats, and let's look at some other examples. Let's just suppose we have different capacities for storing energy, which we do. Okay, that's the case. That's the definition of specific heat. Different capacities for storing energy, and that's, of course, the energy which transfers is called heat, of course. So let's just say it takes 20 minutes to heat up certain mass of water. Doesn't matter the mass. It takes 20 minutes to heat it up to 75 degrees Celsius. Then it takes 4 minutes to heat up the same mass of a different substance, aluminum. Way less time, 4 minutes, 1/5 of the time to get to the same temperature. Same mass of copper, it would take 2 minutes to reach 75 degrees Celsius. 2 minutes to do it. Same mass. So quite a bit, even faster than that, and it would twice as fast as the aluminum. Bottom line is we would say that those ones have a faster ability to heat up and therefore cool off. For that matter, okay, here's a quick table of specific heat values, and I had everyone in class record these down, although the most important one is actually going to be the one on water. We'll use that the most, and almost every other time these specific heat values will be given to you for other substances. But real quick, we just looked at water, aluminum, and copper, and notice the specific heat values. I want to look especially at the joule ones, these units. First, notice the joule units are the units for specific heat. Joules per grams degrees C. Kind of convoluted, but that's how it is with all constants. A specific heat value is considered a constant. It's the letter C, which is handy for the word constant as well. And then the identity will be somewhere in the subscript. So if this were like CH2O, then that would be like the specific heat of water. And so we would use this value when that problem indicates the C of water. Okay. Normally joules per gram degree C is the most important one there. So you got to understand that those are just the units. Anytime you find specific heat, it's joules per gram degree C or calories per gram degree C. Got to pay attention to that top unit, especially because that tells us the units of the heat involved. We'll look at that in a second with a practice problem, and they're from the worksheet posted with the day 1 video and content. So make sure you're looking at that. Of course, that was already assigned in class. Okay, more importantly, to the fact of what was going on with water, aluminum, and copper. We saw that water took 20 minutes to get to 75, aluminum 4 minutes, and copper 2 minutes to get to 75. And notice their specific heat values. Copper has the lowest specific heat. Copper has the lowest specific heat, 0.39. More than double what aluminum's is. Okay, so it has the lowest specific heat, and it went the fastest. So what does that mean? The pattern is, and it happens as it gets lower, it goes faster. Okay, less time. So lower specific heat means less time. Lower specific heat means faster heat up and cool off. Lower specific heat means a lower capacity, lower heat capacity, specific heat capacity. If we think of capacity like a bag with a lesser capacity takes less time to fill up than a bag with a greater capacity would take longer to fill up. So copper, aluminum have a lesser time or lesser heat capacity, therefore a lesser time for heat to fill up its capacity, okay, to meet that capacity top out. So lower heat capacity takes a longer, is faster in a shorter amount of time. I may have said that differently, but lower capacity, shorter time, it's faster. Higher heat capacity takes a longer amount of time to fill up and therefore takes time to heat up. Okay, so good on heat capacity. Rewatch that if you need to. Rewind and go watch it. Let me know what you think about it. Okay. So quick, substance with a large specific heat should heat up slowly. Okay. Ocean water cools, the air gets the warmth. The ocean water cools, that means it loses heat. Where did it lose heat? To the surrounding air. So warms. Sand in the desert is hot in the day and cool at night. Sand means it heats up fast and cools down fast. Must have a low specific heat. So heats up slowly, warms, low specific heat. Pause and reread if you need to. Rewatch too. Measuring heat, we require grams. So measuring heat, we require more than just the capacity is not specific enough. We want to have the specific heat capacity to measure the heat of any sort of circumstance or set. We need the mass, the identity, and the change in temperature as it relates to specific heat. So it requires grams, that's the mass. Temperature change, that's delta T, and that's in degrees Celsius. And the specific heat of the substance, that's a specific heat C value, which is normally going to be given to you in a table or accessible online as well, but it is given to you a table or in the problem itself. So make sure you're looking for that and you're using it appropriately. The equation we have is Q equals MC delta T. Now I want to rewrite this because honestly it's a little clunky here because we use it without the multiplication signs in it. So I want to make sure you see it as it's meant to be and as it's written. I'm going to remove my background here. Q equals MC delta T. That's how we normally write it. M times C times delta T, which is implied because the letters are next to each other. That's just a typical equation, a chemical formula for a chemistry class or a physics class. So make sure you understand that that is what is going on there, and we're going to use that equation to solve the problem. Okay, so that's Q, which is the energy, the heat energy, of course, related here. I showed you on the first video and in Friday's class the Q as it relates to temperature change and things like that. Anyway, here we go. Next up, oops, wrong one. Let's keep going through the slides here. First problem, this is the best way to apply this equation. So 4,000 gram iron poker is left in the fire. How much energy has it absorbed if its temperature increased from 25 degrees Celsius to 90 degrees Celsius? The specific heat of iron is 0.449 joules per gram degree C. Gives you those units, so that tells you the specific heat. So at first, this tells us the 4,000 G, and that is the mass. Should have put the letter first, but I just screwed up on that one. Okay, how much energy absorbed? That is asking for Q. That's the Q part of the equation. Q equals MC delta T. Then it says how much energy has absorbed. So how much energy is the question, so we don't know. If its temperature is increased from, okay, so it says it's increased. That's going to tell us there's a change involved. It's going to be a change in T. However, it changed from a temperature to a new temperature. It doesn't give us the change in temperature, but it implies the change in temperature. So that the initial temperature, Ti, is 25 degrees C. That's why we label it Ti, T subscript I. And the final temperature of the change was 90 degrees Celsius. 90 degrees Celsius, of course, is the higher one. So we could subtract these out. I would normally want to put it on top, but 65 degrees Celsius is where we go with that. You can see M equals 4,000 G, Q, question mark, TI 25, TF 90. I should have put the 90 on top. Subtract to get the change, 65 degrees Celsius. Okay, next it says the specific heat, that's C equals of iron. I could put Fe or C subscript iron is 0.449 joules per gram degree C. Notice I didn't exclude the complicated units there because I wanted you to understand that C is a complicated value, and it's just like all other constants. They kind of are there to help solve the problem and get rid of any any unit issues that we may have. Okay, so let's plug into the equation and solve. Okay, I'm going to let the slides actually guide you through this one. Q equals mc delta T, 4,000 C delta T, the change in. Plug the values in. Sometimes C is capital, sometimes Q is capital, sometimes Q is lowercase. So just understand those are interchangeable. And we get 116,740 joules if you run that calculation. This is just a typical problem-solving calculation. The variable we did not have was Q, so we left it as Q until we plugged in the other variables. It was already isolated, so we just had to do the math necessary to get it to solve for it. Now, getting it isolated still needs to be done because this is an equation, and you must use algebra to solve an equation for a variable. All right, and this one actually shows a good illustration too about how joule values can be so high and are usually so high that we want to use them in kilojoules. So 116.7 kilojoules. Now that doesn't actually match our sig figs. We should only have one sig fig, but we're going to skip that for now because technically I would have wanted to have 3 or 4, and I'm just not illustrating that point at this time. Okay. Another problem, a hot water bottle contains 750 grams of water at 65 degrees C. If the water cools to body temperature, how many calories of heat would be transferred to sore muscles? So the hot water bottle is being applied to a person's body, which was set 37 degrees Celsius. How many calories of heat would be transferred to the sore muscles? Calories of heat would be a Q value, and the specific heat of that water is 1.00 per grams degree C. So the idea is that the water bottle is placed on the body for long enough to achieve the new temperature change or the new temperature value. That's going to give you your change in temperature from 65 down to 37. But still do understand it's final minus initial. Understand, we want to know how much would be transferred to the sore muscles is going to mean the negativity doesn't matter, but notice the change is from 65 to 37. Let me show that just so you can really see what I'm talking about. TF equals 37, TI equals 65 degrees C. So that delta T is actually going to be 37 minus 65, which will give you the negative value, of course. So final temperature it changes down to is 37 degrees C. It's understood that the water bottle will stay on the body until it has achieved that new temperature. So just want to make sure you understand that. And this gives us the specific heat value in calories. So our heat needs to be in calories, and it does ask how many calories. So that's at least helpful for us to pay attention to. Okay, mass is 750. C is 1 calorie per gram. The change, they changed it, just did a general change. This should actually be negative 28 degrees because it's changed to the final temperature. And this negative 28 will make a difference here because you do 750 times 1 times negative 28, and your Q will be negative 21,000 calories. Now, the reason this is because the water bottle has lost 21,000 calories. To what? To the sore muscles, which have gained 21,000. Okay. This question doesn't ask how much heat has the water bottle lost, how much has the muscles gained per se. It just says how much was transferred. So this is one of the cases where the Q value is actually, no matter in or out, plus or minus, is actually equal to the delta H value, which is that enthalpy. That enthalpy mark is, this is the perfect illustration about how Q is H, the enthalpy. Change in heat would just be the transferred heat. Doesn't matter whether it's receiving the heat or losing the heat. The bottom line is the heat transfer is 21,000 calories. If you talked about what was losing or gaining, the water bottle would lose heat. Now this is a good illustration for other things too, but the water bottle loses heat, so its Q value is negative 21,000. Q value for the sore body would be plus 21,000 calories. So just to understand that those are vice versa depending on the system and the setting. The water bottle is the system, it loses negative 21,000. If the surroundings, therefore, are the body, then that gain, that's plus 21,000 calories. So it's worth paying attention to those signs when we talk about that. Now, of course, you could move the decimal, make it 21 kilocalories or big C food calories, and now you've got something to relate to like consumption calories. So that's an interesting way to look at that. Now, understand that heat is a transfer, so there's always a lost heat from one object and a gained heat from another object. This is important, especially because we're talking about, if we talk about another thing called a calorimeter. I'm going to point that out real quick, if you will let me. All right, a calorimeter, much like a thermometer or barometer, barometer pressure, thermometer temperature. This is a calorimeter, is a heat measurer. We're going to learn about this in the calorimetry little assignment on Realize, Kim on Savas Realize. And understand that calorimeter is a heat measurer. That means it actually allows to the measurement of heat. Now it's going to measure the measurement of heat through a change in temperature, and it's going to have some sort of insulating setup. A heat measurer like this is going to have, like a double insulated cup. Normally we can do this in like a lab setting, and we can see a double insulated cup. We want a lid that's loosely bound. We want a thermometer. Okay. Let's see, and we would have a substance in there that's changing temperature. So let's just say we have a certain fluid. Let's call it A and B. So this is how it would look, a double insulated cup there with two substances. We had A in there first, and then B was added later. These would be two different temperature substances, where A is a lower temperature perhaps, and B is a hot substance. We pour in B, and we know the temperatures of both of those, okay? And then essentially the calorimeter allows us to calculate how much heat is lost by the B, the hotter substance, and gained by the A, the colder substance, as they meet in the middle of a certain temperature. So they're both going to have the same final temperature, in which case we can set up a Q equals MC delta T for both substances. So Q for A and Q for B. And we'll understand that Q lost by B is Q gained by A, and we're going to look at that in detail here in a second. So that it would be like this. So B is hotter, and A is the cool substance. Okay, and the temperature measures initially. So we have, say, TA is, let's just say, 20 degrees Celsius, and TB is 75 degrees Celsius. And we have a certain mass of each one. We have mass of A, let's just say, is 100 grams. And mass of B is, let's just say, is 50 grams. All right. And that would be our setup. Okay. Next step we would understand is that the, that's going to be our break time bell. Okay, so TA was, and let's just say we run our experiment. We add B to A inside this calorimeter. This little double insulated situation is called a calorimeter. And we find that the final temperature that they meet at is 37 degrees Celsius. So that'd be the final temperature for both substances. Final temperature for both substances is 37 degrees Celsius. We would do the Q equals MC delta T for each one. Understand that QA would be heat in, and that equals absolute value, of course, QB, whatever it's lost. So we'd say this is the case. QA in is equal to QB out. Sorry, that's sloppy there. And then we just plug in, of course, we want to do absolute value of both of those, sorry. And we'd plug in the MC delta T equation for both scenarios. So that it would be M for A was 100. Let me write this down for all of it. MA times CA times delta T A equals MB times CB times delta TB. And those would equal each other like that. Okay, this is generally how calorimeters work. Plug in is 100. And let's do 4.18 is the C for, they're both waters in this case. Then TA is 37 minus 20, because that's its initial. Then 50 is the mass of B. C is 4.18. And the TB I'm going to put on the next line. Final is 37 minus 75. Now we're going to do absolute value of this, so we're going to get a negative value on one side here, negative value on the B side, but you can understand that is, of course, how that would work. Bottom line is there would be a variable missing in the way this calorimeter would work, and the calorimeter would allow us to solve for the heat lost through the scenarios. Heat was found out through the calorimeter, measure the amount of heat was actually distributed from each one. We would set them equal to each other to find out actually the true final temperature. Ideally, we could set that, we could experimentally decide it as well and compare those values. Pretty useful to kind of see that go down. That's calorimeters. You're going to, of course, explore that in a greater degree in the classroom setting. How about this one? How many kilocalories are needed to raise the temperature of 120 grams of water from 15 degrees Celsius to 75 degrees Celsius? Specific heat is 1 calorie per gram degree C. So, of course, another calorie usage. Pause right now and solve it, and then I'll reveal the answer in the next slide. Of course, use the equation. 7.2 kilocalories. Calorimetry, heat measurement. And next we're going to talk about how heat is added to a heating curve. So I actually want to blow this up really quickly because this is where we're going next. And we're going to do this actually on the next set of slides. Okay, let's resume this real quick. I want to show you another formula so that we can use it to calculate many and various things and parts here. Can you see me? You should be able to see my face in case I need to. Anyway, so we've looked at a heating curve like this before. We looked at this already, and we see that as energy is added across the way, it causes the temperature to rise. And we've put on here that there's a Q value associated with each little section. The Q value with each little section here corresponds to a temperature change. We can now see and relate that means there's an M, mass of how much substance is here. Let's just say this is of water. Okay, it's a heating curve of water, times the C of water, H2O, times the delta temperature change. We can determine the heat of this segment because of the temperature change if we had temperatures plotted along the side, plug in the C value, and if we had the mass of water. Let's just say the mass of water is 100 grams, just for intents and purposes here. Okay, so we're running short on time. Of course, we're going to be coming up at 9:50 for my class, but you'll see this in a second. Q equals MC delta T for these changes here. MC delta T, a different change. Call this delta T1, delta T2. Q equals MC delta T3 here. Bottom line is there's heat, Q, we can solve for each of these different sections here. Now, I want to point out that, yes, we can solve for the Q of each of those sections because they have a temperature change, and we can use that specific heat equation. However, what about the sections for B, C, and D, E? There is still energy added because there's a heat source applying, causing the temperature change initially. That is called the latent heat. There is a certain amount of heat right here, and it is latent. It is lagging behind. There's no temperature that's associated with the heat added on there. The latent heat is what that's called for this non-temperature change related to. Latent heat has its own relationship to mass and the heat capacity, but it uses a different variable. And it uses the variable L fuss for this change. That's fusion or solidification, the reverse. And Q equals ML vap for condensation this direction and vaporization this way. Of course, vaporization would be a positive number. Condensation would be the negative. Fusion, positive. Solidification would be the negative value as well of the same number, of course, for this. Now, we would need a new constant for this L fuss, which is also going to be H fuss at times, and H vap at times. We're going to see those variables plug in as well. So just understand that those are interchangeable with the L, and they still mean we have a constant for L fuss and L vap, and those values need to be looked up on a table and plugged in. Luckily enough for us, we actually have that table on the next slide. And once again, I want to just really reiterate here that this is going on. I'm just going to do the whole screen, and that's going to save it for us. Okay. And go back over here. And understand that we have this table to apply to our L, our heats of fusion. So over here we've got L. Oops, let me plug this in. This is L fuss or H fuss. And this right here is L vap and H vap. They're the same thing, of course. And these values are in kilojoules per grams, which also means joules per gram, and that way those units satisfy our equations. Once again, this is just a different unit. We're going to practice this some more tomorrow. I'm going to reiterate the point on latent heat. Latent heat allows us to plug in Q values for ml fuss and ml vap, and we can find the Q heat that was actually done during this section. We can find the Q amount of heat for this section, DE and BC. Because there's no temperature involved, we can't use the MC delta T equation to find the Q. We need to actually use the, sorry, I need to actually do this real quick. Because there's no temperature involved, we need the actual Q, ml vap, ml fuss, etc. there. So just want to clear that up for you. Make sure we're on the same page. That concludes our lesson for this topic on latent heat and whatnot. And there's our time for the video. Go Dogs. Take a look at it. Let me know what you think, and we'll pick up from there.